Inside the world's busiest candy lines, everything from the crisp punch of Nerds to the rainbow pop of Skittles begins with the same fierce mix of heat and precision. Sugar cores grow, coatings build in layers, and huge color drums spin these treats into their signature textures and shines. In this documentary, we trace the hidden steps that shape each candy's identity and reveal how factories turn simple ingredients into global icons. The Nerds production process begins with the selection and preparation of the sugar crystal cores. Unlike many candies that use molded or extruded centers, Nerds start with what are essentially coarse grains of sugar, clean, dry, and free of additives. These tiny sugar granules are screened to ensure uniform starting size. They must be small enough to grow consistently in a panning environment, yet large enough to withstand dozens of successive syrup applications without dissolving prematurely or becoming structurally unstable. The sugar cores are transported via vibratory feeders into stainless steel holding hoppers, where they await transfer to the coating pans. The pans used in Nerds production are large, tilted, rotating drums, often made of polished stainless steel or copper-lined interiors, mounted on motorized axles. Each pan is loaded with a pre-measured volume of sugar cores, and as they begin to rotate, the motion causes the particles to tumble and circulate continuously, exposing all surfaces evenly. This rotation is crucial. It ensures that every granule is coated uniformly on all sides, preventing clumps, deformities, or pooling. As the pan turns, a fine mist of sugar syrup is sprayed into the chamber using precision-controlled nozzles mounted near the drum's edge. This syrup, the heart of Nerds' layering process, is a concentrated solution of sugar and water, cooked to a specific temperature that ensures viscosity without excessive runniness. It's critical that each application is delivered in ultra-fine mist form. If too much syrup is added at once, the granules will clump or flatten. If too little is applied, the layer won't spread or bind evenly. The candy makers apply the syrup in short bursts, followed by a drying cycle. To dry each layer, warm dehumidified air is pumped into the pan, either through ducts that lead directly into the chamber or through perforated side vents that circulate around the rotating drum. Each coating cycle, spray, tumble, dry, adds only a fraction of a millimeter of mass to each piece. The factory repeats this cycle dozens of times, building up the candy shells layer by layer until the particles reach their desired diameter. Because Nerds aren't smooth or spherical, but instead irregular and jagged, the motion of the pan is calibrated to encourage slightly chaotic collisions. This helps preserve the rough texture and prevents the shells from polishing themselves into uniform spheres. It's a balance of engineering and deliberate imperfection. Once the pieces reach mid-size, flavoring is introduced. The flavoring agent, usually a concentrated blend of acids, natural or artificial flavors, and a small amount of binding sugar, is mixed into the syrup and sprayed as a component of the next several layers. The inclusion of citric, malic or tartaric acid in these syrups is what gives Nerds their intense tanginess. The acids aren't just flavor additives, they also influence the syrup's drying behavior, and they react slightly with the sugar during curing, adding complexity to the texture and finish. Each flavor batch is kept isolated in its own production cycle. For example, the grape batch and the strawberry batch are never made in the same pan at the same time. Color is added as part of the flavoring syrup or in a dedicated later cycle. High-intensity food-grade dyes are introduced in micro quantities and bond to the exterior of each piece during the drying process. The rotating motion ensures even color coverage across all pieces. If needed, a polishing agent like carnauba wax is added at the end to give the pieces a slight gloss and improve pourability and packaging flow, but unlike smoother candies, Nerds are not excessively polished. Their irregularity is part of their design, and over-polishing would compromise the tactile crunch consumers expect. Once the candies have completed their panning and drying sequence, they are transferred via air ride conveyors or vibratory chutes into sieving units that sort them by size and shape. Undersized particles or pieces fused during the coating process are separated and removed. These may be reprocessed, used in bulk product, or discarded depending on their condition. The main batch continues into temporary holding bins, which act as buffers between panning and packaging. These bins are kept sealed, dry, and mildly climate controlled to prevent any reabsorption of moisture. The packaging process for Nerds is as specialized as the candy itself. Each traditional Nerds box features 2 flavors separated down the middle. This requires a dual hopper system where 2 vibratory feeders, each calibrated for a different flavor, dispense products simultaneously into twin funnels that lead to either side of the box. Boxes are pre-formed from flat stock using a carton erecting machine. The boxes are folded, glued, and printed on site with all product information, flavor names, batch codes, and nutritional data. As the boxes move along the packaging belt, they pass under the dual dispensing nozzles. Each side of the box is filled with exact amounts of its designated flavor, controlled by a combination of weight sensors and timed release gates. Once filled, the box passes through a closing mechanism that folds and seals the top flap, usually with pressure adhesive. After sealing, the boxes are printed with the final production time and batch number using thermal inkjet printers and are diverted to an automated case packing station. Boxes are arranged into cartons using robotic arms that layer them in specific formations designed for stability during transit. Each carton is scanned for completeness, sealed with tape or hot glue, and labeled for inventory tracking. Cartons are palletized in predetermined stacks and shrink-wrapped for storage. Final product pallets are stored in ambient conditions away from direct light and heat sources to preserve color and flavor. Throughout this entire operation, each machine is monitored by an industrial control system that logs key variables such as drum rotation speed, syrup pump flow rate, drying air temperature and humidity, flavoring concentration, and piece weight. If any variable drifts outside its preset tolerance, alarms are triggered, and either adjustments are made automatically or the line is stopped for inspection. In-process quality assurance includes routine sampling of product from each batch. Selected pieces are tested for moisture content using Carl Fisher titration, checked for weight uniformity, color intensity via spectrophotometers, and hardness via compression testing. Flavor strength is assessed by trained sensory panelists who taste test small samples for tanginess, sweetness, and balance. Batches that don't meet standards are flagged for rework or disposal. Samples are retained from every lot in a traceability vault where they're stored for months in case of consumer inquiry or recall verification. Sanitation of equipment between flavor runs is critical. The panning pans are flushed with warm water, scrubbed manually or by automated spray heads, and dried thoroughly. Transfer lines and feed hoppers are vacuumed, wiped, and swabbed for allergen residue, particularly if fruit flavors alternate with sour or spicy variants. All cleaning is verified using protein or ATP tests before a new flavor run can begin. Because Nerds have such intense color and acidity, even a tiny bit of cross-contamination could discolor or distort the taste of a new batch. Production lines can be scaled depending on volume requirements. For seasonal or limited edition batches, smaller coating pans and micro-dispensing stations are used. For high-volume standard runs, like grape and strawberry, multiple pans operate in parallel with synchronized drying and transfer systems, feeding a centralized packaging hub. This modularity allows the factory to adapt batch sizes without compromising efficiency. Unlike other panned candies that are polished to a near mirror-like finish, Nerds maintain their chaotic and crystallized texture because the syrup formulations are designed to dry unevenly, creating edges and ridges that catch the tongue and amplify the sensory crunch. The layers aren't perfectly smooth and are never compressed, only dried and allowed to harden naturally. This gives the candy its unique tactile appeal. Skittles begin with the creation of their chewy interior core, which is essentially a sugar-based gel formulated for elasticity, density, and controlled chewiness. This core mass is created in large stainless steel cooking vessels equipped with steam jackets that allow precise temperature control during the preparation of the base. The basic ingredients, granulated sugar, corn syrup, and water, are measured automatically by weight sensors and pumped into the vessel, where they're heated while constantly agitated to prevent scorching or uneven caramelization. The temperature is carefully elevated to dissolve the sugar fully and initiate a Maillard reaction-free blend, ensuring that the final texture remains pale and neutral, ready to absorb added color and flavor later. As the syrup cooks, continuous stirrers move through the mix to keep solids suspended evenly. The goal is a thick, clear candy gel that can be cast into molds while retaining its shape and resilience. Once the mass reaches its target viscosity and concentration, it is cooled slightly and pumped through heated pipes to a flavoring station. There, rotating blending heads introduce pre-measured amounts of flavor oils and acid blends to create each Skittles flavor: strawberry, orange, grape, lemon, green apple, and others, depending on the mix. The flavoring is added while the base remains hot to allow complete integration, but cool enough to avoid evaporating volatile components. The flavored mass is divided into color-coded batches, each handled separately. From here, the hot candy is portioned into small droplets using a starch molding system. Large trays of dry cornstarch are stamped with shallow cavities using custom metal boards shaped to the exact dimensions of a Skittle interior. As the trays move along a belt, a depositor head above the line releases precise amounts of the hot syrup into each starch pocket, forming hundreds of raw candy centers per tray. The starch absorbs surface moisture and provides a non-stick bed for the candy to set. Once filled, trays are stacked into large drying tunnels where they are left undisturbed for up to 2 full days. Warm, low humidity air flows through the chambers in controlled patterns, drawing out moisture from the centers gradually to preserve their elasticity while building up a denser outer layer. This results in a finished center that is soft but firm enough to retain its shape under mechanical stress later in the process. After curing, the trays are fed into a starch removal system. High-powered air blowers, rotating brushes, and vibrating sifters remove residual starch from every piece. The clean centers are now semi-finished candies, chewy tablets without any shell or color. They're separated by flavor batch and transferred via inclined vibrating conveyors into large stainless steel holding hoppers, where they're prepared for the shell building stage that gives Skittles their iconic look and texture. The next phase is sugar shelling, or panning. This process takes place in large rotating pans, angled drums fitted with smooth interiors that allow candy pieces to roll and tumble freely without becoming damaged. Each pan is dedicated to a single flavor to avoid cross-contamination. Thousands of centers are loaded into each pan, which slowly rotates on its axis, creating constant motion across the mass. A fine spray of sugar syrup, made from a blend of sucrose, glucose, and water, is gently misted over the tumbling centers via precision nozzles. Immediately after each spray, dry sugar is dropped into the pan to bind to the surface of the syrup. A blast of warm, dehumidified air is pumped into the chamber to dry the layer instantly. This process, syrup, sugar, drying, is repeated dozens of times over several hours. Each application adds a microscopically thin layer of sugar to the surface of every candy, gradually building up the hard, crunchy shell that surrounds the chewy interior. The tumbling motion ensures even coverage and encourages the natural formation of slightly curved, asymmetric shapes that Skittles are known for. Unlike perfectly round candies, Skittles are meant to have slight natural variation, which enhances their sensory appeal when poured, handled, and chewed. Once the base white shell has been built, colorants are added in the final layers. These colors, vibrant purples, reds, oranges, yellows, and greens, are mixed into a final set of sugar syrups and applied using the same spray and dry sequence, but in tighter, faster rotations to lock in the color before it runs or pools. This layering technique allows for deep color saturation without creating thick outer shells. Each color batch is processed separately, and equipment is cleaned between runs to prevent color bleeding or flavor confusion. After the last color layer is applied and dried, the candies move to a polishing pan. A small amount of carnauba wax or a food-grade polishing glaze is misted over the rotating candies, which are tumbled slowly in low-heat conditions to spread the glaze evenly. This produces the glossy finish Skittles are known for and improves the handling and flow of the product during packaging. The wax coating also acts as a moisture barrier, extending shelf life and preventing stickiness in humid environments. At this stage, Skittles are visually complete but not yet branded. For that, the candies are sent to a high-speed printing line. The signature S logo is printed onto each piece using edible white ink, delivered by specialized inkjet heads that can stamp thousands of pieces per minute. The candies move under the printer on narrow tracks that separate them just enough to expose the surface. Sensors detect orientation and adjust the print head as needed to ensure the S is centered on each piece. After printing, the candies are allowed to rest briefly in shallow bins to allow the ink to fully dry and bond to the shell. Once dry, all colors are recombined into a multi-flavor blend by feeding them into a wide mixing chute where precise volumes of each flavor are blended according to recipe. Sensors verify that the correct ratios are being maintained, and camera systems ensure color consistency throughout the mix. Blended candies now move to the packaging stage. Skittles are offered in various sizes, from single-serve pouches to large resealable bags and novelty containers. Each format has its own automated line. All begin with a multi-head weigher, a machine that uses a series of load cells to determine the exact amount of candy to release into each package. Dozens of weigh hoppers are filled and recalibrated multiple times per second to ensure that each pouch receives a consistent net weight. The weighed candies fall through chutes into form-fill seal machines that create bags from roll stock film. This film is unwound, shaped into a tube around a filling nozzle, and heat sealed at the bottom to create a pouch. The candy drops in immediately after, and a top seal is applied, finishing the package. A notch is cut for easy opening, and in resealable formats, a zipper or adhesive strip is pressed into the film just before the top seal. Each sealed pouch is printed with a production date, expiration date, and batch number using thermal or laser printing units. They then pass through metal detectors and X-ray scanners to ensure no foreign objects are present. Any pouch that fails the inspection is automatically ejected from the line. Verified packages are moved onto robotic palletizers, where they are sorted into boxes or cartons depending on shipping format. The cartons are sealed, stacked on pallets, and stretch wrapped for shipping. Some pallets are routed directly to distribution centers, while others are stored in warehouse inventory. The warehouse conditions are temperature and humidity controlled to preserve the integrity of the sugar shells and to prevent color fading or moisture pickup. At every stage of this process, from syrup cooking to final packaging, data is recorded and tracked in a central control system. This includes temperatures, weights, drum speeds, spray times, drying durations, color intensity scores, and batch traceability markers. Each component is monitored to prevent deviation, and any anomaly, whether in syrup viscosity or final product gloss, is flagged by the system and reviewed by technicians. Sanitization between batches is managed using clean-in-place systems for pipes and tanks, and full manual cleaning for tumblers, dryers, and packaging stations. After each run, pans are emptied, washed with heated water, sprayed with food-safe detergents, and dried using forced air. Color stations are scrubbed thoroughly to prevent cross-contamination, particularly between flavors that use sensitive dyes or volatile oils. M&Ms begin with the core of the product, milk chocolate that must be formulated, tempered, and molded into small lentil-shaped pieces before the colorful candy shells can be applied. The chocolate is produced in dedicated chocolate-making facilities that start with cocoa liquor, cocoa butter, sugar, milk powder, and emulsifiers, all of which are carefully metered and blended together in high-capacity mixers. The cocoa liquor itself is prepared by grinding roasted, winnowed cocoa nibs into a thick paste. This paste, rich in both cocoa solids and fat, is mixed with sugar and milk solids to form the base of milk chocolate. The mixture passes through a series of refining rollers to reduce the particle size to under 20 microns. This critical threshold ensures that the final chocolate has a smooth, creamy texture when consumed. Once refined, the mix enters large conching machines, heated steel vessels with rotating arms that knead the chocolate slowly for hours, evaporating unwanted acids, enhancing flavor, and encouraging even distribution of the cocoa butter across all particles. This process can last for 6 to 24 hours, depending on the desired flavor profile and chocolate texture. After conching, the chocolate is tempered. This process uses carefully controlled heating and cooling cycles to stabilize the cocoa butter crystals into the correct polymorphic form, known as Form 5, which provides the finished chocolate with its signature glossy appearance, firm snap, and resistance to blooming. The tempered chocolate is now ready to be molded into the M&M centers. To create the core shapes, the chocolate is deposited into rotary molding drums. These are chilled stainless steel or polycarbonate molds arranged on a wheel or carousel system. As the tempered chocolate is portioned out by depositor heads, it fills lentil-shaped cavities with exact mass. The molds rotate through a refrigerated chamber that cools the chocolate evenly from all sides, causing it to solidify into firm, smooth discs. Once cooled, the chocolate pieces are demolded and released onto conveyors. From here, the molded chocolate centers are sent into a conditioning tunnel where they are stabilized at a consistent ambient temperature to equalize internal stresses and prepare the surface for coating. The now solid chocolate lentils are poured into large revolving coating pans, which are the heart of the shell application process. Each pan is a large, angled, spinning drum where the pieces tumble continuously in a gentle motion. In these pans, the sugar shells are applied through a process called hard panning. The panning process begins with the application of sugar syrup, a concentrated solution of sucrose, glucose, and water. Nozzles spray the syrup onto the tumbling chocolate pieces in timed bursts, ensuring a very thin, even coating across all surfaces. After each syrup application, dry powdered sugar is introduced to absorb the moisture and initiate crystallization. Warm, dry air is blown into the pans to dry the coating quickly. This spray-dry cycle is repeated many times, gradually building up the hard, crunchy shell around the chocolate core. Each layer adds just a fraction of a millimeter to the total size, so dozens of layers are required to reach the final shell thickness. The tumbling motion ensures even coverage while preventing the candies from clumping or sticking together. Operators carefully monitor syrup flow rate, pan speed, and air temperature to maintain consistency across millions of individual pieces. If too much syrup is applied at once, it can cause pooling, lopsided shells, or color unevenness later in the process. Once the desired shell thickness is reached, coloring begins. Food-grade dyes specific to each M&M color, red, yellow, blue, green, brown, and orange, are introduced as part of a final sugar coating stage. The dyes are added either directly to the syrup or sprayed separately between final sugar layers to lock in the color. The timing of color application is crucial. It must occur after the shell has enough structure to support liquid application, but before final drying and polishing. Each color batch is processed separately to prevent crossover. Once the color has dried and bonded to the outer sugar layer, the pieces move to the polishing stage. A polishing solution, often containing carnauba wax or a similar food-safe glaze, is applied in small amounts to the candy while it tumbles in polishing pans. The motion smooths out any residual roughness and creates a glossy, hard finish that resists moisture and improves shelf life. The polishing process also ensures that the M&Ms have the signature reflective sheen that sets them apart from dull-coated products. After polishing, the candy is allowed to cool and set. Batches of each color are stored in temporary silos or bins where they're held under controlled temperature and humidity to stabilize the shells before printing. Printing is handled by high-speed rotary inkjet printers that stamp a white M onto each piece. The candies move on wide, vibrating conveyors, passing under print heads that are aligned to detect the center of each candy and apply the M with precision timing. The printing ink is edible, fast-drying, and specially formulated to bond with the candy shell without smudging or rubbing off during packaging. To ensure complete coverage, each printer is synchronized to hit the top face of the lentil shape, which is tracked using cameras or mechanical positioning sensors. The result is consistent logo placement with minimal rejection rates, even at speeds of tens of thousands of pieces per minute. After printing, the candies are ready to be mixed. M&Ms are known for their assorted colors, so dedicated blending machines are used to combine exact proportions of each color into a consistent mix. Color metering chutes control how much of each shade enters the final stream, and photo sensors validate that the blend meets the target ratio. The mixed candies then move to the packaging line. The packaging phase varies depending on product format. Individual servings, sharing bags, and bulk formats each require different equipment. At the start of this phase, multi-head weighers measure precise amounts of product using multiple load cells arranged in combination patterns. These weighers can make rapid decisions to select the best combination of hoppers that add up to the target weight, often accurate to within 1/10 of a gram. Once weighed, the candies fall into vertical form-fill seal machines that form a pouch from flat plastic film, seal the bottom, release the candy, then seal the top and apply a tier notch. For rigid containers, like tubes or cartons, robotic arms deposit the candy into pre-formed packaging before sealing with foil, plastic lids, or induction seals. Each pack is printed with production codes, expiration dates, and batch numbers for traceability. Filled packs pass through quality control stations that include metal detectors and X-ray scanners to ensure no foreign materials are present. Sealed bags are checked for leaks using pressure tests and often weighed again to confirm accuracy. Packs that pass are grouped into cartons using robotic case packers, labeled and palletized. Pallets are shrink-wrapped and stored in temperature-controlled warehouses to prevent shell degradation or fat bloom on the chocolate core. Throughout this process, data from every step is captured in the factory's SCADA system. Operators track temperature profiles during chocolate tempering, monitor panning duration, shell thickness, syrup concentration, and dye ratios. Real-time analytics allow for micro-adjustments to maintain consistency across thousands of kilograms of candy produced per day. Sanitation procedures are also highly standardized. All equipment is made from food-grade stainless steel and is disassembled or flushed between batches. Water lines and syrup pumps are cleaned with detergent cycles, and pans are scrubbed and visually inspected before reuse. Flavor or color transitions require dedicated cleaning cycles to avoid trace contamination, especially when switching between seasonal colors or limited edition batches. Lindt chocolate is produced in a tightly structured factory process that begins with the transformation of raw cocoa beans into ultra-fine, smooth, and creamy chocolate using specialized machines, proprietary techniques, and finely tuned timing sequences that preserve the delicate flavors of cocoa while eliminating bitterness and grit. The process begins when whole dried cocoa beans arrive at the factory in large bulk containers and are conveyed directly into storage silos built to maintain low humidity and a stable temperature to prevent any premature oxidation or moisture absorption. From these silos, the beans are measured out by weight and directed into a cleaning unit where vibrating screens, air classifiers, and magnetic separators remove stones, dust, string, and any foreign matter so that only clean beans proceed to the next step. The cleaned cocoa beans are then transferred to a batch roaster or continuous drum roaster, which exposes them to dry hot air with precise temperature control and rotation speed to ensure the beans are heated evenly from all sides. Roasting develops the flavor of the cocoa, reduces astringency, and darkens the color of the nibs inside the shell. The temperature and duration of roasting are carefully controlled depending on the variety and origin of the bean, and are adjusted based on moisture content and desired flavor profile. Once roasted, the beans are cooled rapidly using forced air to prevent over-roasting, and then they move to the winnowing machine. The winnowing process cracks each roasted bean and separates the outer shell from the nibs inside. This is done using mechanical rollers that crush the beans gently, and blowers that blow away the lighter shells while heavier nibs fall into collection bins. The winnowed nibs are what contain the cocoa solids and cocoa butter required for chocolate production. These nibs are directed into large grinding chambers where rotating steel drums or stone rollers crush them into a thick, dark, gritty paste known as cocoa liquor. This liquor is then pumped into a series of high-pressure hydraulic presses that separate the fat from the solids. The fat becomes cocoa butter, while the remaining cake is pulverized into cocoa powder. In parallel, whole milk powder, sugar, and additional cocoa butter are stored in bulk hoppers and prepared to be added to the chocolate base. The exact formulation depends on whether the chocolate being made is milk, dark, or white. For milk chocolate, cocoa liquor is blended with sugar, milk powder, and cocoa butter in large horizontal mixers until a uniform paste forms. This coarse chocolate mass is then sent to the refining stage. Refining involves passing the chocolate paste through a sequence of steel rollers that reduce particle size. Each roller set progressively narrows the gap, crushing sugar crystals and milk particles until they are reduced to between 15 and 20 microns. This ultra-fine particle size is critical for the mouthfeel of Lindt chocolate, ensuring there is no graininess when the chocolate melts on the tongue. The refined chocolate then moves to the conching stage, which is one of the defining steps in Lindt production. Conching is done in elongated mixers called conches that slowly knead the chocolate at elevated temperatures, typically between 45 and 80 degrees Celsius, for several hours or even days, depending on the recipe. The purpose of conching is to develop flavor and texture. During this phase, volatile acids and off flavors are driven off by heat and agitation, while the friction created by the mixing reduces viscosity and smooths the fat dispersion. This stage also transforms the aroma profile, eliminating any lingering bitterness or sharp notes and rounding out the flavor. In Lindt's process, conching is considered both a science and an art, and the parameters are adjusted delicately to reflect the cocoa origin, sugar type, and desired smoothness. Once the chocolate mass has reached the optimal flavor and flow characteristics, it is transferred to tempering machines. Tempering is a controlled heating and cooling cycle that aligns the cocoa butter crystals into a stable form, known as form Vi. This ensures that the finished chocolate will have a glossy finish, a crisp snap, and will not develop bloom or grayish streaks over time. In the tempering machine, the chocolate is first heated above the melting point of all cocoa butter crystals, then cooled to a point where only form 5 can reform, and finally reheated slightly to working temperature. During this process, precise control of temperature and agitation is vital. Tempered chocolate is now ready for molding or enrobing. For bar production, tempered chocolate is poured into polycarbonate molds, which are vibrated on automated shakers to remove air bubbles and allow the chocolate to settle evenly into every corner. The molds are then passed through cooling tunnels, where cold air gradually lowers the chocolate temperature until it sets and solidifies. For filled chocolates or truffles, the molds may first receive a thin shell of chocolate, which is cooled and then filled with soft centers like ganache, praline, or liqueur before being sealed with more chocolate and cooled again. Once the chocolate has solidified, the molds are inverted and gently flexed by mechanical arms or vibration plates to release the bars or pieces. These are conveyed through a final inspection area where high-speed cameras and vision systems scan for imperfections such as broken corners, air pockets, or deformed logos. Defective. Pieces are rejected automatically, and perfect pieces proceed to wrapping. Wrapping is tailored to the product type. Lindt bars are typically wrapped in foil, followed by an outer paper sleeve. Machines cut foil to precise dimensions, fold it tightly around each bar, and then apply the paper wrapper using hot glue or pressure-sensitive rollers. Filled chocolates and balls are often wrapped in twisted foil ends or sealed flow packs using high-speed rotary packaging machines. Each wrapped unit is date-coded and batch-labeled for traceability. The wrapped chocolates are grouped into cartons by robotic arms that use suction cups to pick and place items into retail display boxes or shipping trays. Cartons are sealed, labeled, and palletized on automated stations where stretch wrap secures the load for transport. Pallets are scanned, assigned barcodes, and stored in climate-controlled warehouses to preserve flavor and appearance. The ambient temperature is maintained between 15 and 18 degrees Celsius with low humidity to prevent sugar or fat bloom from forming. Throughout the entire process, every parameter, from roast temperature to conche duration to tempering curve, is logged and monitored by a central control system. Inline sensors track viscosity, temperature, and particle size, while samples are pulled regularly for lab testing. These lab tests include moisture content, flow behavior, flavor analysis, and crystal structure confirmation to ensure the chocolate meets Lindt's quality standards. Chocolatiers also perform sensory evaluations, tasting samples for balance, aroma, melt, and finish. Hygiene and cleaning are equally critical in the production line. Chocolate making equipment is cleaned between product changes using melted cocoa butter flushes, which push out remnants of previous batches, followed by food-grade detergent cycles and high-pressure rinse systems. All cleaning is validated with swabs and lab tests to prevent flavor, cross-contamination, and microbial growth. In factories producing multiple chocolate types, changeovers are scheduled with precision to minimize downtime. Dark chocolate lines are usually run first, followed by milk, and then white chocolate, since darker varieties are more difficult to flush from equipment. Any chocolate not meeting specification during changeover is reworked or diverted to non-retail uses. Each ingredient in Lindt chocolate is treated with care. Sugar is milled to uniform crystal size and stored in dry silos with dehumidifiers. Milk powder is kept in oxygen barrier bags to preserve freshness. Cocoa butter is melted and filtered through fine mesh screens to remove impurities before blending. Even inclusions like nuts or fruit are roasted or candied on site to preserve their crunch and freshness. and they're added via gravity feeders that deposit precise amounts into the mold as chocolate flows in. The finished product that arrives on shelves results from a careful sequence where every gram of chocolate has passed through dozens of machines, heat cycles, mixing steps, and quality gates to guarantee it matches Lindt's profile for shine, snap, aroma, and flavor. From bean to bar, the chocolate moves with purpose through a network of conveyors, tanks, rollers, pumps, sensors, and skilled calibration, ensuring that what ends up in the foil wrapper is not just chocolate, but a refined and deliberate experience. Hershey's chocolate is manufactured through a large-scale factory process that transforms raw agricultural ingredients into solid molded chocolate bars, using a continuous sequence of heating mixing, refining conching, tempering molding, and packaging that is engineered for consistency, scale, and shelf life. The process begins with the intake of whole, dried fermented cocoa beans that are sourced in bulk and delivered in freight containers to the processing facility, where they are offloaded using vacuum conveyors or bulk tipping systems into steel silos designed for moisture protection and temperature stabilization, so the beans are kept in ideal condition before production begins. From these silos, the beans are moved into a cleaning station where mechanical sieves, air separators, and magnetic traps remove foreign matter such as twigs, dust stones, and bits of string. And the cleaned beans then enter large batch roasters or continuous flow roasting drums where hot air is circulated through the rotating chamber to heat the beans evenly and activate the chemical changes responsible for chocolate flavor and aroma. The exact roasting temperature and time are carefully controlled to vary the flavor strength depending on the blend being produced, and the roasted beans are then cooled quickly using forced air or vacuum systems to lock in the desired profile and prevent overdevelopment. Next, the cooled roasted beans pass through a cracking and winnowing machine where roller blades break the shells apart, and airflow systems separate the lighter papery husks from the heavier cocoa nibs, which contain the actual cocoa solids and cocoa butter required for chocolate production. The separated nibs are collected and sent to grinding chambers, where heavy granite rollers or steel grinders crush them into a thick, dark paste known as chocolate liquor, which is not alcoholic, but simply refers to the pure ground state of cocoa solids suspended in their own fat. At this stage, the chocolate liquor is held in heated storage tanks, where it can be separated into cocoa butter and cocoa solids if necessary, using hydraulic presses or used directly in chocolate mass formulation. The chocolate base used for Hershey's milk chocolate typically includes chocolate liquor, sugar milk, powder, cocoa butter, and sometimes emulsifiers to improve flow properties. And in this stage, these raw materials are measured precisely using load cells and volumetric dosing systems before being transferred into industrial blenders, where they are mixed at high speeds into a coarse brown paste. The sugar crystals are still relatively large at this point, and the milk powder has not fully hydrated, so the mixture is lumpy and thick. But the goal of this step is to distribute the ingredients uniformly before refining. The refining process consists of passing the chocolate paste through a 5-roll mill or similar refining system, which crushes and shears the mixture repeatedly until all particles are reduced to between 15 and 20 microns in size, which is below the threshold of perception on the human tongue and is responsible for the smooth texture of finished chocolate. The refined powdery mass exits the rollers as dry flakes, which are collected and fed into large conching vessels, which are long horizontal mixers with heavy paddles that knead the chocolate continuously while applying gentle heat. Conching is one of the most important steps in the process and can last from several hours to a full day, depending on the batch size and the desired flavor characteristics. And during conching, the frictional heat softens the cocoa butter, allowing it to coat sugar and milk particles completely. While the mixing action evaporates unwanted volatile acids that contribute bitterness, and also promotes chemical bonding between ingredients that gives chocolate its rounded flavor and creamy mouthfeel. In Hershey's process, this stage may include the addition of flavor compounds or the use of proprietary heating profiles that contribute to the distinctive, sweet, slightly tangy note associated with their milk chocolate. After conching, the now liquid chocolate mass is pumped through a fine mesh filter to remove any remaining solids and then enters the tempering system, which is a temperature-controlled series of heat exchangers and holding tanks that bring the chocolate through a controlled heating and cooling cycle designed to stabilize the cocoa butter crystals into the desired form V structure, which provides gloss snap and resistance to fat bloom. The tempering process requires careful monitoring of viscosity temperature, shear rate, and time to produce a chocolate that will remain stable during storage and distribution. Once tempered, the chocolate is moved into the molding line where it is dispensed into bar molds, using precise portioning heads that fill each cavity to the exact weight required. And the filled molds are shaken on vibrating tables to eliminate air bubbles and ensure even distribution of the chocolate across the mold. The molds then pass through a cooling tunnel where refrigerated air is circulated in stages to gradually bring the chocolate down to the release temperature, allowing it to solidify without developing stress cracks or surface bloom. When the chocolate has fully set, the molds are inverted and the bars are ejected using mechanical arms or flexing systems that pop the finished bars onto conveyor belts for inspection. Every bar passes under a series of vision systems that scan for surface defects, broken edges, misaligned logos, or irregular thickness, and any bar that fails inspection is automatically diverted for rework. Acceptable bars move forward to the wrapping section, where high-speed machines fold foil or film around each piece and seal it using heat or pressure depending on the packaging format. Paper sleeves or cardboard cartons are then applied and printed with product information barcodes and expiration dates using inline inkjet or laser printers. Wrapped bars are grouped into shipping cases by robotic packing arms and loaded onto pallets, which are stretch wrapped and labeled for traceability before being moved into temperature-controlled storage rooms maintained between 15 and 20 degrees Celsius to preserve texture and flavor. From this point, the bars are distributed through refrigerated trucks or ambient carriers depending on shelf life and destination requirements. In parallel with production, the entire process is monitored by sensors that record key data at every stage, from ingredient weight and tank temperature to roller pressure and mold cavity fill speed. And this data is fed into a centralized quality control platform that logs all production variables and triggers alerts if any parameter drifts outside the approved range. Quality assurance teams sample bars from each batch and test them in laboratories for moisture content, melt profile, flavor, strength, hardness, and microbiological stability. And these tests ensure that every bar maintains the same quality level regardless of where or when it is produced. All equipment used in the chocolate production line is constructed from food-grade stainless steel and is subject to strict sanitation protocols between product runs. Clean-in-place systems flush liquid chocolate from pipes and tanks using melted cocoa butter, followed by hot detergent solutions and sterile water rinses. And these cleaning cycles are verified using swab tests and microbial analysis before the next production run begins. During cleaning, mechanical components such as belts, pumps, and seals are inspected for wear and lubricated with food-safe oils to maintain performance and prevent contamination. Because Hershey produces multiple chocolate types, including dark white and flavored variants, the factory must perform regular changeovers that are scheduled with precision to minimize waste and avoid flavor crossover. And this is typically done by running from the lightest product to the darkest, so that any residual ingredients are less likely to impact flavor in the next batch. Storage of ingredients is just as critical as processing, and milk powder is kept in dehumidified silos lined with oxygen barriers, while cocoa butter is stored in heated jacketed tanks that maintain a constant liquid state, and sugar is held in dry bins fitted with vibratory feeders to ensure consistent flow into the mixers. Even inclusions like almond toffee or cookie pieces are added through dedicated feeders designed to introduce solids at the molding stage without disrupting flow or causing jams. From beginning to end, Hershey's chocolate production line is a finely tuned balance of mechanical engineering, food science, and sensory evaluation, where the transformation of beans into bars depends on maintaining strict control over texture, flavor, and structural integrity. The iconic bars that result are the outcome of thermal history particle refinement, fat crystallization, and packaging precision that together produce a chocolate that is consistent across millions of units and recognized by consumers around the world. Godiva chocolate production begins with the careful handling of raw cocoa beans, which arrive at the factory in bulk loads from cocoa-growing regions and are stored in cool, dry silos that prevent moisture contamination, oxidation, and pest activity. These beans are first cleaned through mechanical sifters that remove stone shells dust and organic debris using a series of vibrating screens, suction fans, and magnetic traps. Once cleaned, the beans are weighed and portioned by automated systems and conveyed to the roasting chambers, which are precision-engineered rotating drums capable of uniform thermal penetration across the entire mass of cocoa beans. Roasting is the first flavor-developing stage in the chocolate-making process, and in the Godiva production method, it is carried out at moderate temperatures for extended periods, which helps preserve the aromatic volatiles while driving off unwanted acidity and bitterness. Each batch is roasted based on its origin and moisture level, with constant temperature regulation using internal thermocouples that feed data to a computerized control system. Once the beans are fully roasted, they are immediately cooled with forced air systems that halt the roasting curve and stabilize the volatile compounds formed during heating. The next step is winnowing, which involves cracking the roasted beans open to separate the brittle shells from the cocoa nibs inside. The beans pass through a mechanical cracker that gently fractures them, and a pneumatic winnower that blows the lighter shells away while the heavier nibs fall into collection bins. These nibs are the core ingredient in all chocolate and contain both cocoa solids and cocoa butter in their natural ratio. The nibs are routed to a pre-grinding unit where rotating stone rollers or steel discs crush them into a thick, gritty paste known as cocoa liquor. This liquor is heated slightly to reduce viscosity and then transferred to high-pressure hydraulic presses that squeeze out the cocoa butter, leaving behind a dense cake of compressed solids which are ground into cocoa powder. For milk chocolate production, the cocoa liquor is blended with refined sugar, high-quality milk powder, additional cocoa butter, and in some recipes, a hint of vanilla or lecithin, which acts as an emulsifier. Each ingredient is dosed using gravimetric feeders and poured into large, high-speed mixers where they are combined into a smooth, uniform brown paste. This initial chocolate mass is far too coarse to be palatable, so it is sent to the refining system. This consists of a 5-roll mill where the mixture passes between sets of rollers that progressively reduce the particle size down to below 20 microns, creating a texture that feels smooth and creamy on the tongue. After refining, the powdered chocolate mass is transferred into conching machines, which are large horizontal vessels with internal mixing blades that work the chocolate slowly while applying gentle heat. This process can take anywhere from 12 to 24 hours, depending on the desired flavor profile, and is critical for developing the smooth texture, deep aroma, and balanced flavor that distinguishes Godiva from other mass-market chocolates. The conching action evaporates undesirable acids and moisture while distributing the cocoa butter evenly over every particle, which contributes to the distinctive mouthfeel and melt of the final product. Once conching is complete, the chocolate is sent through a filtration unit to remove any remaining impurities and then proceeds to the tempering stage, which is one of the most technically precise parts of the entire process. Tempering involves heating the chocolate to above its melting point, then cooling it down to initiate the formation of stable cocoa butter crystals known as Form 5, and then slightly reheating it to a working temperature, where those crystals can be maintained in suspension. This controlled crystallization ensures that the finished chocolate will have a glossy sheen, a crisp snap when broken, and a long shelf life without the development of sugar or fat bloom. The entire tempering process is carried out in enclosed stainless steel tanks equipped with agitators and digital thermostats that keep the temperature profile exactly within a 1 degree tolerance. The tempered chocolate is now ready for molding or enrobing. For solid chocolate bars or shapes, the tempered chocolate is poured into precision-engineered molds made of food-grade polycarbonate. These molds are vibrated to remove air bubbles and ensure that the chocolate spreads evenly into every corner and detail of the design. The filled molds then pass through a cooling tunnel that gradually lowers the temperature, allowing the chocolate to solidify and contract slightly so it can release cleanly from the mold. The pieces are then turned out and conveyed to the packaging line. For filled chocolates like pralines, truffles, and caramels, the process adds additional steps. The mold is first coated with a thin layer of tempered chocolate using spinning or tilting mechanisms to create a uniform shell. This shell is cooled just enough to firm up and then filled with liquid centers like ganache hazelnut paste or fruit cream using precision nozzles that deliver exact volumes to each cavity. Once filled, the chocolates are sealed with a final layer of chocolate and sent through a second cooling tunnel to solidify completely. These filled chocolates are then demolded and sent to wrapping. Enrobed chocolates, such as chocolate-covered nuts or biscuits, are passed on a conveyor belt under a waterfall of tempered chocolate where they are coated completely and pass under a vibrating plate that ensures even coverage and allows excess chocolate to drip off. The enrobed pieces then pass through a cooling tunnel similar to the molded chocolates where the coating solidifies uniformly. Wrapping is carried out using high-speed automated systems that use foil or flow wrap depending on the product. Each chocolate is first wrapped in an inner layer to preserve freshness and then given an outer wrap or box depending on whether it's a single piece or part of a collection. These wrappers are applied using thermal sealers and folded precisely by mechanical arms to maintain presentation quality. The finished chocolates are grouped into assortments using pick-and-place robots that load them into rigid trays or decorative boxes, which are then closed, labeled, and shrink-wrapped for transport. Throughout the entire production process, quality control is integrated into every stage. Inline sensors measure parameters like particle size, viscosity temperature, and moisture content. Random samples are taken and tested for flavor consistency, flow behavior, microbiological safety, and visual appearance. Each batch is tracked from bean to box using barcode systems and digital batch records, which allow full traceability and accountability. Any deviation from the strict specifications results in automatic rejection and investigation to maintain the high quality associated with Godiva. Packaging lines are designed not only for speed, but also for delicate handling. Chocolates are not simply dropped into boxes, but placed gently by grippers or vacuum arms to prevent any scuffing or deformation. Seasonal and limited edition boxes are assembled by dedicated packaging stations that include decorative inserts, gold leafing, or ribbon application, all of which are coordinated with the central production database to match inventory with demand forecasts. Finished products are palletized automatically and moved to cold storage areas where the ambient temperature is held between 15 and 18 degrees Celsius with low humidity to protect against fat bloom sugar crystallization or flavor degradation. Logistics systems monitor inventory in real time and coordinate dispatch using climate-controlled vehicles that ensure the chocolates arrive at retail destinations in pristine condition. Factory sanitation is handled with clean-in-place systems for all enclosed equipment and rigorous manual cleaning protocols for all external surfaces. Between product types, especially when transitioning from dark to milk or white chocolate lines, are flushed with cocoa butter and inspected using allergen tests to confirm no cross-contamination occurs. Equipment such as molds tempering tanks and piping is made from food-grade stainless steel and is subject to frequent validation, including swab tests, microbiological plating, and ATP analysis. Each product that leaves the factory reflects a meticulously controlled combination of mechanical design, sensory expertise, thermal precision, and ingredient handling, all executed on a scale that allows handcrafted quality to meet global demand. Godiva's reputation depends on this balance, where artistry meets automation, where every bar and truffle is not only shaped by steel and steam, but guided by formulas and feedback that ensure every box offers the same refined, luxurious experience no matter where it is opened. Spam canned meat begins its manufacturing process with chilled pork cuts entering the initial reduction line, where rotating blade assemblies slice the dense blocks into manageable segments that can feed smoothly into the primary grinder. The grinder's helical screw immediately draws these pieces forward, pressing them through a precision-drilled plate that creates uniform meat particles. And this uniformity allows the next mixing stage to distribute additives consistently. These freshly ground particles move directly into a temperature-controlled mixing chamber, whose jacketed walls circulate coolant to maintain a low and stable temperature, ensuring that the proteins do not smear or break down during agitation. As the ground meat settles inside the chamber, automated ingredient dispensers positioned above it release a measured sequence of salt, curing elements, sugar, and additional stabilizing agents, and the moment these ingredients fall in, a pair of interlocked ribbon paddles begins a slow, synchronized rotation designed to pull material from the outer walls toward the center. This inward folding pattern repeats continuously, which gradually builds a uniform matrix of meat and dissolved additives, and that uniform matrix prepares the mixture for vacuum treatment. Once the system's sensors detect that mixing torque has stabilized, an indicator of proper consistency, the vacuum lid seals over the chamber and the air extraction pump begins lowering internal pressure. As the pressure drops, microscopic bubbles rise from the paste and collapse on the surface, and this removal of trapped gases compacts the mixture into a dense, cohesive phase that will later hold its shape inside the can. When the vacuum cycle completes, hydraulic actuators tilt the entire mixing vessel forward, guiding the meat paste toward a stainless steel discharge chute. This chute leads the paste directly onto an enclosed transfer conveyor whose internal airflow is tightly controlled. And this enclosure prevents temperature fluctuations as the paste moves toward the portioning system. As the conveyor delivers the mixture into the depositor's intake manifold, a series of metering cylinders opens to receive it, each cylinder equipped with a sliding gate and a vertically driven piston. These cylinders fill one after another until integrated load cells confirm that each chamber holds the exact programmed mass, and once this mass is reached, the sliding gates close to isolate the measured portions. Meanwhile, empty cans advance along a parallel conveyor that narrows into single-file alignment, and as they move, they pass through filtered air jets that clear their interiors of loose dust or microscopic particles. This preparation ensures that when the cans reach the filling zone, each one is ready to receive its measured charge of meat paste without interference. The two conveyors meet at the depositor, where each can is precisely positioned beneath a cylinder's outlet by a mechanical indexing arm that pushes the cans into perfectly spaced pockets along the line. As soon as a can reaches the correct location, the piston above it begins its downward motion, forcing the compact meat paste into the metal cavity in a single continuous stroke, which eliminates voids and establishes the characteristic block-like internal structure. When the piston retracts, a fixed wiper blade scrapes the cylinder's interior surface to prevent residue buildup, and this ensures that every subsequent portion enters the next can with the same exact mass and texture. Once filled, the cans transition onto a settling conveyor equipped with a low-frequency vibration plate. This plate applies gentle vertical oscillations to the freshly filled cans, allowing the paste to settle and eliminate microscopic gaps that may still remain after piston filling, and the stabilized contents prepare the cans for immediate sealing. As the cans leave the settling area, they enter a high-speed seaming machine, where a preformed metal lid is dropped precisely onto each rim, while a rotating chuck and roller assembly crimps the lid's edge into the can body. This forming operation creates a gas-tight double seam, and the uniformity of this seam is essential for the next major phase, thermal processing. Once sealed, the cans enter a continuous retort system, a long, tunnel-like chamber where steam or superheated water circulates around rotating baskets that hold the cans. As the baskets move, every can experiences consistent heating, and this heat penetrates the dense meat block, activating the curing reactions and stabilizing the proteins while rendering the final texture. The retort maintains precise time and temperature conditions so that each can reaches the target internal temperature at the correct rate. And this controlled heating transforms the formerly soft paste into the firm, sliceable form associated with the product. When the thermal cycle ends, the cans exit the retort and immediately enter a cooling zone where chilled water sprays reduce their temperature in stages, preventing sudden contraction that could deform the seam. After cooling, the cans move onto an air drying conveyor, where high-velocity fans remove surface moisture to prepare them for labeling. The dry cans then enter the labeling carousel, which applies adhesive-backed wraps that align perfectly using optical registration sensors, ensuring each label sits squarely against the cylindrical surface, without wrinkles. As the labeled cans rotate through the carousel, pressure rollers press the labels firmly to guarantee complete adhesion and a smooth exterior finish. Once labeling is complete, the cans advance toward the inkjet coating station. Here, a high-resolution nozzle prints alphanumeric production information onto the top or bottom surface of each can. The printer synchronizes its spray pulses with the conveyor's exact speed so each code lands consistently in the same position. Immediately after printing, a short section of forced air nozzles dries the ink before the cans make contact with any guiding rails, preventing smudging during the remainder of the line. With coating complete, the cans reach the final inspection conveyor. A series of sensors check seam integrity, label placement, fill height, estimated through weight readings, and can dimensions. Any can falling outside the allowed tolerance triggers an automated pusher arm that diverts it from the main flow. The accepted cans continue onward to the packaging assembly, where they enter a carton forming machine. This machine erects flat cardboard blanks into open cartons using vacuum grippers and folding rails. And once the cartons hold their shape, the cans slide into them in tightly organized rows. As the cartons fill, an overhead flap folder closes the top panels while a gluing station applies a thin line of adhesive. Compression belts then squeeze the cartons briefly to activate the bond. The sealed cartons immediately transition to a palletizing system. This system arranges the cartons layer by layer onto large pallets using a pattern that maximizes vertical stability during transport, and each layer aligns precisely with the next through mechanical guides that keep the arrangement square. Once the pallet reaches its programmed height, a wrapping arm encircles it with stretch film, stabilizing the entire load for movement. The finished, fully wrapped pallets then roll onto the outbound conveyor, completing the transformation from raw pork cuts to fully processed, thermally stabilized, sealed, labeled, coated, and packed canned meat. Smoked salmon begins its manufacturing process with whole chilled fillets entering the trimming line, where a synchronized set of blade assemblies removes the thin belly membrane and levels the surface of each fillet to create a consistent starting geometry. This geometry is crucial because it determines how evenly the salt mixture will absorb later. So immediately after trimming, the fillets slide onto a conveyor that positions them for the pinbone extraction machine. Here, a series of narrow, oscillating grippers aligns over the muscle surface, gripping and lifting each pinbone in a single upward pull. This extraction eliminates hard points that could interrupt the uniform curing and slicing process downstream. Once trimmed and deboned, the fillets enter the curing section. A volumetric salt dispenser releases measured layers of salt and sugar over the conveyor belt, and the fillets pass beneath its nozzles, so each surface receives an exact dosage. As soon as the salt mixture makes contact, a mechanical arm flips each fillet to coat the opposite side, ensuring symmetrical curing. The salt crystals immediately begin drawing moisture from the muscle fibers, and this moisture migrates toward the surface, dissolving the crystals into a brine layer. To control this reaction, the fillets move into a stacked curing tunnel. In this tunnel, multiple perforated trays hold rows of fillets while a constant airflow passes over them. This airflow pulls excess moisture away and maintains a stable environment, allowing the muscle proteins to tighten and form the firm, translucent texture associated with smoked salmon. As curing progresses, the brine that forms on each fillet drains into collection channels beneath the trays. These channels lead to a filtration chamber where the liquid's density and conductivity are measured. Although the brine is discarded, the sensor data ensures that each batch reaches a consistent cure level before exiting the tunnel. When the curing cycle finishes, the trays slide onto an outbound lift that lowers them to the rinsing line. Here, a set of low-pressure water jets washes the residual surface salt from the fillets without disrupting the internal gradient created during curing. The water jets oscillate side to side, covering every region of each fillet. After rinsing, the fillets pass through an air knife dryer, where high-velocity sheets of air remove excess surface moisture and prepare the flesh for the drying stage. The dried fillets enter a dehydration chamber equipped with long horizontal racks that move forward in slow increments. Within the chamber, controlled heat and airflow create a narrow humidity band that gently reduces water activity. This step tightens the muscle structure even further, which allows smoke particles to adhere more effectively later. As the fillets travel through the chamber, internal moisture equalizes from center to exterior. By the time they exit, each fillet has reached the ideal pre-smoking firmness. Immediately after dehydration, the fillets pass into the smoking system. This system is a multi-zone chamber divided into sections that control smoke density, airflow direction, and temperature independently. The first zone introduces a thin, mild smoke created by controlled smoldering of hardwood chips inside a sealed generator. The smoke enters through overhead ducts and spreads evenly across all racks. As the fillets move forward, they encounter the second zone, where smoke density increases and recirculating fans push air diagonally across the racks to ensure complete surface exposure. Temperature remains low, so the flesh does not cook. Instead, the smoke compounds slowly bind to the proteins, forming the glossy outer layer characteristic of smoked salmon. The final smoking zone shifts airflow to a vertical pattern. Fans pull smoke downward across the fish, penetrating any microgrooves in the muscle surface. The chamber's sensors track particulate levels continuously, adjusting feed rates so each batch receives consistent exposure. By the time the fillets exit the smoking chamber, they exhibit a uniform color gradient and a stabilized texture that can withstand mechanical slicing. The smoked fillets then travel to a brief cooling tunnel where chilled air circulates around them to halt further smoke absorption. The cooling also firms the muscle, which enables cleaner cuts in the slicing stage. As each fillet cools, it is transferred onto a wide conveyor that feeds into the slicing preparation unit. This unit aligns fillets lengthwise using adjustable side guides. Once aligned, an overhead scanner maps the fillet's dimensions, determining thickness variations that could influence slicing pressure. With dimensional data collected, the fillets advance toward the horizontal slicer. This machine uses a rapidly vibrating blade or multi-blade band system that creates thin, even slices with minimal pressure. The oscillation speed keeps the blade from dragging through the flesh, producing smooth surfaces. As the blade moves, each slice falls gently onto a receiving belt positioned below the fillet. This belt is coated with a non-stick surface, so slices do not fold or stretch. A secondary belt intersects at a shallow angle and transfers the slices in a neatly fanned arrangement. This arrangement maximizes visibility and uniformity for packaging. Once sliced, the salmon enters the portioning zone. Laser-guided weigh cells determine how many slices make up the programmed portion weight, and conveyor actuators separate the slices into exact groups. These portions move forward onto chilled stainless steel plates that stabilize the slices while the vacuum packager prepares the film. Above the plates, a sheet of high barrier film unwinds between two tension-controlled rollers, maintaining consistent thickness and preventing wrinkles. The plates then slide beneath the film, and the chamber closes over them. Inside the vacuum packager, air is extracted from the sealed chamber, causing the film to drape tightly over the salmon slices. Once vacuum reaches the set value, a sealing bar applies heat around the pack's perimeter, bonding the film to the lower tray. The chamber then releases, and the packages exit onto a cooling conveyor, where cold air vents help the sealed film re-harden and maintain shape. After cooling, the packages move beneath a printer that adds production codes and traceable identifiers in a uniform location. With coding complete, the packages travel through an inspection array. Multiple sensors evaluate seal integrity by measuring how the film reflects laser light. If any section deviates from the expected pattern, the system flags the package and removes it from the line. The remaining packages continue toward the cartoning machine. This machine erects cardboard sleeves and inserts the sealed packs into them using sliding rails. The sleeves close around the packs, forming rigid, stackable units. The carton packs then advance to a shrink-wrapping tunnel. Here, a thin layer of polymer film forms a tight secondary wrap around multiple cartons at once, stabilizing them for palletizing. The film shrinks under warm air jets and contracts uniformly around the load. Next, the stabilized multi-packs reach the palletizer, where mechanical arms lower each group into a structured pattern on a pallet deck. Once enough layers accumulate, a rotating arm dispenses stretch film to lock the full pallet together. Returning to the earlier stages, the process can be understood as a continuous sequence where each transformation prepares the salmon for the next. For example, the trimming ensures clean edges that allow salt to contact evenly. The curing step modifies water distribution across the flesh, increasing firmness so the fillets can tolerate the dehydration chamber's airflow without warping. Dehydration, in turn, creates a surface environment ideal for smoke absorption. Smoke exposure produces a protective exterior that both contributes flavor and stabilizes the fillet for slicing. That stabilized texture then enables the slicing blades to glide without tearing, producing aesthetically consistent pieces. Packaging locks in these qualities by removing oxygen and sealing moisture, and the final palletizing step ensures the product remains structurally stable during distribution. Each component in this chain depends on the previous one functioning precisely, For instance, the air knife dryer, before dehydration, removes free water that would otherwise block smoke adhesion. The scanner before slicing collects geometric data that allows the slicer to adjust blade angle and oscillation speed. The laser seal inspection verifies that vacuum packaged trays maintain internal negative pressure, preventing unwanted changes to texture. Even transitions between steps contribute to consistency. Conveyors connecting curing, rinsing, drying, smoking, and slicing maintain uniform spacing and synchronized speed so fillers never bunch or overlap. In the smoking system, airflow patterns shift gradually, ensuring that smoke density changes do not shock the fillers and cause uneven absorption. Cooling tunnels introduce chill in stage temperature bands, preventing rapid contraction of the smoked flesh. Further upstream, the curing tunnel's brine drainage pattern ensures that salt contacts both sides of each fillet evenly over time. The perforated trays allow moisture to escape uniformly, reducing pooling that could disrupt the curing gradient. Downstream, the slicing portioner uses real-time weight calculations to maintain consistent package weights, even if individual slices vary slightly in thickness, due to natural variations in the fillet. Finally, each process concludes by stabilizing what the previous one created. Curing stabilizes moisture, drying stabilizes texture, smoking stabilizes the exterior protein structure, cooling stabilizes slice quality, and vacuum packaging stabilizes the final product against environmental changes. Chicken breasts begin their manufacturing process as chilled, whole muscle portions move from bulk bins onto the initial alignment conveyor, where parallel guide rails orient each piece in the same direction to prepare them for precision trimming. The trimming machine uses a series of synchronized rotary blades that contour along the natural shape of the breast, removing residual skin, excess fat, or uneven edges, so the muscle presents a consistent thickness for all downstream steps. As each trimmed piece leaves the blade assembly, it transitions onto a weigh belt, whose integrated load cells capture mass data in real time, allowing the system to sort the breasts toward different processing paths based on their size profile. Once sorted, the chicken breasts advance to the surface inspection module. Overhead, scanners emit a structured pattern of light that maps each fillet's geometry, measuring thickness, curvature, and moisture sheen. The resulting data determines how the fillet will be oriented for the tenderization stage. The conveyor adjusts its speed to ensure spacing between fillets, keeping each breast centered beneath the next mechanical unit. When a fillet reaches the tenderizer, two opposing roller heads covered with evenly spaced protrusions lightly compress the muscle fibers. This compression standardizes texture and promotes even absorption during subsequent marination. Directly after tenderization, the breasts enter the injection system. Here, a horizontally oriented manifold holds dozens of thin, hollow needles aligned in a grid pattern. As the fillets pass beneath them, the conveyor pauses momentarily while the needles descend into the muscle. Pressurized pumps deliver a calibrated solution, often containing water, salt, and functional ingredients, through the needles into the interior of each breast. The injection system monitors internal pressure to prevent overfilling and ensures that the distribution remains uniform throughout the muscle. When the needles retract, the conveyor restarts and sends the breast toward the tumbling drums. The tumbling drums rotate slowly around a horizontal axis, their interior surfaces lined with lifting baffles that scoop and drop the chicken repeatedly. This tumbling motion distributes the injected solution evenly and allows the muscle fibers to relax, improving texture. The drums operate under vacuum, removing trapped air from between muscle layers and enhancing the efficiency of the tumbling action. As the drum completes its cycle, a discharge door opens and the breasts slide onto a perforated conveyor where excess liquid drains away before the next processing stage. Following tumbling, the breasts enter a flattening system designed to create uniforms, thickness across all pieces. 2 parallel belts run through a narrowing gap, pressing each breast gently but firmly as it passes. Sensors above and below the belts measure compression force and automatically adjust the belt spacing. This guarantees a uniform surface thickness, which will later allow consistent thermal processing and slicing if required. Once flattened, the fillets move towards the portioning unit. The portioner uses a combination of vision scanning and dual blade cutters to segment each breast into precise shapes or weights, depending on the intended final product. For example, a large breast may be divided into multiple uniform cutlets. The scanning system builds a 3D model of each fillet's profile, determining the optimal cutting lines for maximum yield. Rotary blades then execute each cut, while the fillet is kept motionless by a short vacuum hold on the conveyor. The cut pieces drop onto a secondary belt that organizes them into rows for further processing. At this point, the breasts may undergo surface seasoning. A dry ingredient applicator deposits an even curtain of powdered seasoning across the conveyor. The fillets pass beneath the curtain, where the powder adheres to the slightly tacky surface left from the tumbling process. A vibrating platform beneath the belt helps distribute the seasoning uniformly, preventing clumping. An air knife station then removes excess particles, ensuring consistent coverage. Next, the breasts enter the forming and shaping line. This system uses a high-pressure forming chamber to shape pieces into standardized contours if the product requires precise geometry. The breasts slide into molding cavities created inside a chilled forming plate, and a top plate descends to apply uniform pressure. The muscle conforms to the cavity shape, and after a brief hold, the mold opens, pushing the shaped portions onto a release belt. This shaping improves the predictability of cooking and slicing patterns later. From shaping, the chicken breasts move toward the thermal treatment area. The first step is preheating, where the fillets pass through a controlled warm air tunnel that brings their surface temperature to a precise range. This prevents shock when they enter the main cooking chamber. The preheated breasts continue onto a multi-zone oven with separate temperature and airflow controls. The first zone rapidly increases internal temperature through forced convection. The second zone stabilizes the temperature rise to prevent overcooking on the exterior. The third zone holds the chicken at its target core temperature long enough to achieve structural firmness. Inline temperature probes mounted on robotically positioned arms insert into sample breasts at intervals to verify that the oven settings align with the internal heating model. These probes transmit data instantly to the oven's control module, which adjusts airflow, humidity, and heat output to ensure uniformity across the entire batch. As the cooked breasts exit the oven, they enter a rapid cooling tunnel where chilled air streams across both sides of the fillets to lower their temperature quickly, locking in texture and preventing residual cooking. If the product requires slicing, the cooled breasts drop onto the slicing conveyor. A high-speed blade assembly cycles through several thousand oscillations per minute, producing clean cuts with minimal pressure. The slicing unit uses sensors to map each breast surface and adjust blade angle to maintain consistent thickness across every slice. As slices fall onto the belt below, they arrange automatically into overlapping shingled patterns using a series of angled guide plates. This pattern makes packaging easier and ensures visual uniformity. If the product remains whole, the breasts bypass the slicer and continue toward the surface freezer. This system uses extremely cold air circulated at high velocity to chill the outer layer of each fillet just enough to stabilize its shape. This process, known as crust freezing, prevents deformation during packaging and helps maintain the precision of portions created earlier. Once properly cooled or crust frozen, the breasts enter the packaging line. Here, they move into a vacuum sealing machine equipped with multiple forming pockets. Each pocket holds a single breast or sliced portion. The bottom film pulls tightly into the pocket to create a tray-like shape, and the chicken breast settles into this molded film. A top film then drapes over the product, and the chamber closes. Air extraction creates a vacuum that tightens the film around the product. A heat seal bar bonds the edges of the film layers, locking the product inside an oxygen-reduced environment that preserves texture. After sealing, the packages travel along a cooling belt to allow the film to contract evenly. The next station is the print coder, where inkjet nozzles apply product information and production identifiers onto each package. Optical sensors verify print legibility and alignment. Packages with misprints are diverted by a pneumatic pusher arm that only activates for items exceeding the coded tolerance. The accepted packages then move into the inspection unit. X-ray scanners evaluate internal density to identify bones or foreign matter. Because chicken breasts vary naturally in density, the scanner uses an adaptive algorithm tuned to muscle structure. Any package showing an anomaly is removed automatically. Approved packages proceed toward the carton loader. The carton loader erects flat cardboard blanks into open containers using mechanical folding arms. The vacuum-packed chicken slides into these cartons via a sloped feeding chute, and adhesive applicators seal the top flaps. The cartons then pass through a bundling station where they group into sets. A shrink-wrap film encircles these groups, and they enter a heat tunnel where warm air shrinks the film tightly around them. Once bundled, the cartons advance toward palletization. A robotic arm lifts each bundle and places it onto a pallet following a precise stacking pattern optimized for stability. Layer by layer, the stack grows until it reaches the programmed height. When complete, an automated stretch wrapper encircles the entire pallet with a spiraling sheet of film that secures the load. Chef Boyardee beef ravioli begins its industrial journey with the delivery and preparation of raw ingredients in a tightly controlled, high-capacity food processing environment designed for continuous, large-scale output. At the very start, durum wheat semolina arrives in bulk and is stored in tall silos connected by enclosed pneumatic systems that transport measured amounts of flour into industrial mixing vats. These mixers operate under vacuum to prevent air entrapment in the dough, which could compromise the texture of the final pasta. Water is injected through a flow-regulated system, and the dough is mixed into a dense, elastic mass that is then conveyed into a dough sheeter. Inside this machine, large stainless steel rollers gradually press the dough into a long, uniform sheet of precise thickness. Sensors constantly monitor and adjust roller pressure, sheet thickness, and alignment in real time, ensuring consistent dimensional control across thousands of linear feet of pasta every hour. As the pasta sheet continues on its route, it approaches the forming station. Here, the sheet is split into top and bottom layers using a synchronized cutting system, and the beef filling, prepared simultaneously on a parallel line, is introduced between them. The beef mixture is produced in massive steam-jacketed kettles, where ground beef is cooked with tomato paste, spices, salt, and stabilizers. High-shear mixing blades ensure uniform blending, while thermal sensors regulate the internal temperature to avoid overcooking. Once cooked, the beef filling is transferred to positive displacement pumps that feed the filling directly into the ravioli former. Precise nozzles inject a consistent amount of filling at evenly spaced intervals onto the bottom sheet. The top sheet is laid over it, and the two layers are pressed together by a rotary die that seals and cuts the individual ravioli pockets in one continuous motion. Any excess dough around the edges is collected and recycled back into the dough feeder. The freshly formed ravioli travel along a mesh belt through a par cooking tunnel, where a curtain of low-pressure steam partially cooks the pasta just enough to firm the structure and set the seal. The par cooking chamber is followed by a high-efficiency air chiller that quickly cools the product to prevent further cooking. From here, the ravioli move to the accumulation table that feeds the canning line. The tomato sauce, which is made in a separate set of kettles, is already being prepared in parallel. This sauce includes tomato puree, vegetable oil, spices, and sugar, blended in high-capacity vats, equipped with wall-scraping agitators to ensure uniform cooking and prevent scorching. The sauce is filtered to remove any large solids, skins, or seeds, and is kept hot in jacketed holding tanks while waiting to be dispensed. The canning line is a seamless, high-speed process that brings ravioli and sauce together inside sterilized metal cans. Empty cans are first fed from depalletizers into an inverted position for steam or air sterilization before being returned upright and carried along a conveyor. A timed filling system first drops a preset quantity of ravioli into each can. Next, a separate nozzle dispenses a specific volume of hot tomato sauce into the same can. Load cells and vision sensors measure weight and volume in real time, instantly rejecting any can that falls outside tolerance. To maintain long shelf life, the filled cans receive a quick injection of steam into the headspace to displace oxygen, which is critical for preventing spoilage and discoloration. The cans then proceed to the seaming machine, which applies and crimps the metal lids at high speed using rotary chucks that spin and press the lids into place with a hermetic seal. Once sealed, the cans are routed into a massive rotary retort, a large pressure chamber where the canned ravioli undergo commercial sterilization. This thermal processing step is one of the most critical phases in the entire operation. Inside the retort, the cans are exposed to pressurized steam at temperatures above 121 degrees Celsius for a fixed period, calculated according to product density, can size, and altitude. The process is tightly controlled by a programmable logic controller that adjusts heat input, steam pressure, and timing with precision, ensuring that the interior of each can reach the temperature needed to destroy any potential microbial contaminants. This sterilization method allows the product to be shelf-stable for over a year without the use of chemical preservatives. As the cans exit the retort, they are rapidly cooled using a countercurrent water system that brings the internal temperature down quickly while avoiding thermal shock that could warp the can. After cooling, the cans are dried using air knives that blow off any surface moisture. They then move into the labeling area where each one is printed with a unique production code, expiration date, and batch number using high-speed inkjet printers. These codes are logged in a centralized database that allows full traceability of every can, linking it back to the exact batch of dough, filling, sauce, and sterilization cycle. This traceability system is essential for maintaining quality control and complying with food safety regulations. Labels are applied using rotary labelers, which align the cans, dispense the adhesive-backed labels, and press them smoothly onto the curved surfaces. Any can with a misapplied or missing label is automatically diverted off the line. The labeled cans proceed to the packing station, where they are grouped into shrink-wrapped multi-packs or loaded into cardboard trays, depending on distribution requirements. Robotic arms equipped with vacuum suction heads stack these cases onto pallets in a tightly packed, interlocked pattern that ensures transport stability. Each pallet is weighed, stretch-wrapped, and labeled with a scannable barcode that encodes the full logistics data for shipping and warehouse integration. Completed pallets are conveyed into a climate-controlled warehouse area, where ambient temperature is maintained within a narrow range to preserve product integrity and packaging quality. The inventory system automatically logs each pallet into a virtual grid based on product type, batch, and destination. Orders from distribution centers are matched against inventory using software that assigns retrieval instructions to automated guided vehicles. These vehicles transport the pallets to loading bays where they are prepared for shipment on temperature-managed trucks. Throughout this entire process, every step is monitored by industrial control systems that log thousands of data points per minute, from moisture content in dough to the pressure in the retort chamber. If any sensor detects an anomaly, whether it's a filling inconsistency, temperature deviation, or mechanical irregularity, alarms are triggered, and corrective protocols are initiated automatically. Quality assurance technicians also perform random sampling at every stage, testing dough elasticity, filling viscosity, source pH, seam width, and internal vacuum levels. Any sample that fails a parameter prompts an investigation and potential quarantine of the related batch. The design of this factory setup allows for continuous production for 24 hours a day, with modular maintenance schedules that let individual lines shut down without halting the entire operation. Cleaning in place systems run through every tank, pipe, and pump at regular intervals, using cycles of hot, caustic solution, followed by acid rinses and pure water flushes. This level of automated sanitation prevents bacterial buildup and maintains a sterile environment, especially critical in the post-cook zones. By the time a single can of Chef Boyardee beef ravioli reaches the supermarket shelf, it has passed through dozens of machines and control checks, undergone multiple thermal transformations, and been assembled from raw materials that were processed, cooked, combined, sealed, and sterilized within minutes of each other. The result is a uniform, shelf-stable product that replicates the exact same taste, texture, and aroma across millions of cans each year, a feat of engineering, timing, and integrated automation performed at industrial scale. The industrial production of gnocchi begins with a continuous intake of raw potatoes selected specifically for their starch content, moisture levels, and uniformity. These potatoes arrive in bulk, often delivered in heavy-duty totes or truckloads, and are immediately transferred into stainless steel receiving bins. From here, a water flume system propels the potatoes toward the washing stage using a circulating stream of filtered water, which not only moves the product gently, but also performs a preliminary rinse that separates dirt, rocks, and field debris. The potatoes pass into a rotary drum washer, a large cylindrical cage lined with soft baffles and rotating paddles. Inside, multiple high-pressure spray jets clean the surface of every tuber, while slow drum rotation ensures even exposure. Wastewater is filtered and recycled back into the flume, maintaining efficiency while minimizing fresh water consumption. Once cleaned, the potatoes move onto inclined conveyor belts and pass beneath an optical sorter that detects misshapen or heavily blemished specimens. Air jets eject any defective potatoes instantly. The remaining load proceeds toward the steam peeling chamber, a sealed environment into which high-pressure steam is injected rapidly. This process loosens the skins in seconds without penetrating deeply into the flesh. A sudden pressure drop follows, causing the skins to rupture. As the chamber releases its load, rubber fingers or gentle high-pressure sprayers remove the loosened skin without damaging the underlying structure. The peeled potatoes then travel along a belt for final inspection before cooking. Next, they enter a cooking tunnel equipped with rotary steam ovens or belt-fed boiling sections. These systems are calibrated to cook each potato evenly, using internal probes to track core temperature without overcooking the starch. The cooking time is precisely tuned so the flesh softens just enough for mashing while preserving structural integrity. Cooked potatoes are discharged directly into screw-fed conveyors that deliver them into industrial mashing systems. These mashers force the hot potatoes through perforated plates using rotating paddles, breaking them into a uniform, lump-free mash with consistent density. This mash is transferred into stainless steel hoppers, fitted with agitators to prevent settling while it awaits mixing. Simultaneously, dry ingredients are prepared using a separate set of feeders. Wheat flour, salt, and any dry seasonings are metered in precise ratios using volumetric or gravimetric dispensers, ensuring repeatable consistency across large batches. These dry components meet the hot mash in horizontal ribbon mixers or twin screw extruders, where the dough is developed. If eggs or other binders are used, these are injected through nozzles timed to match the flow rate of the dry and wet components. Dough temperature, torque, and consistency are continuously monitored, allowing automated systems to adjust mixing speed or ingredient dosing in real time. As the dough reaches its final form, it exits into forming lines. These lines are fitted with multi-head extrusion units that shape the dough into cylindrical ropes, which are automatically guided into a cutting module. Guillotine blades or rotary knives slice the ropes into uniform pillow shapes at high speed. Each piece is then transferred onto a vibrating sorting table to prevent clumping and ensure even spacing before shaping. For traditional gnocchi, a patterned drum or stamp roller presses the surface of each dumpling, forming the signature ridges. These ridges aren't just for appearance. They help hold sauces and ensure the texture is consistent during cooking. The raw gnocchi are now ready for par cooking. Depending on the product type, they may enter a steam tunnel, boiling water bath, or continuous blanching system. For fresh gnocchi, a short steam treatment helps gelatinize the starch on the outer layer, setting the shape without fully cooking the interior. In the case of shelf-stable or refrigerated products, boiling is used for more complete cooking. The gnocchi travel through the system on mesh conveyors that allow water to drain or steam to vent. Those that float prematurely, often indicating trapped air or structural failure, are skimmed off and diverted. Finished gnocchi are cooled rapidly with air or chilled water sprays to stop the cooking process immediately. Cooling is followed by drying. Par-cooked gnocchi are passed through air tunnels or oscillating belts with forced, filtered airflow. This surface drying stage ensures the pieces don't stick together in packaging. In some configurations, a fine coating of semolina or rice flour is applied to further reduce surface tackiness. At this stage, the gnocchi are fully formed, partially cooked, and ready for packaging or freezing depending on the final product category. Fresh gnocchi are directed into multi-head weighing systems that portion exact quantities into pre-formed pouches. These machines calculate the best weight combination from multiple hoppers to ensure precision. Pouches enter a modified atmosphere packaging (MAP) chamber, where the ambient air is replaced with a mix of inert gases like nitrogen and carbon dioxide. This extends shelf life by inhibiting microbial growth and oxidative reactions. Sealing jaws then close each pouch under pressure, forming airtight seals. Pouches exit the MAP system and are immediately inkjet printed with production codes, expiration dates, and batch tracking information. For frozen gnocchi, the cooled pieces bypass MAP and instead travel to the freezing tunnel. This is a long conveyor system housed within an insulated chamber where fans blow extremely cold air across the product. The process is known as IQF, or individual quick freezing, which ensures that each gnocco freezes separately, avoiding clumps. Once frozen solid, the gnocchi are packaged in bulk or consumer-ready bags, sealed, labeled, and sent to deep freeze storage. Regardless of the format, every package goes through a metal detection and X-ray inspection station before final packing. These machines identify any potential contamination from production, like stray metal fragments from worn machine parts, and immediately reject any affected units. Packages that pass inspection proceed to robotic case packers, where arms equipped with vacuum grippers load them into cardboard boxes. The boxes are sealed, barcoded, and sent to automated palletizers that stack them according to optimized loading patterns. Each pallet is stretch wrapped and labeled with a traceable QR code or barcode, then entered into the warehouse management system. The final stage is cold storage and distribution. Refrigerated products are stored at 2 to 5 degrees Celsius, while frozen products are kept at 18 or colder. High-density shelving is managed by ASRS units, automated storage and retrieval systems, that navigate the warehouse floor with programmed efficiency. When an order is placed, the system retrieves the correct pallet, stages it at the loading dock, and synchronizes it with outbound transport logistics. Goods are typically moved in temperature-controlled trucks that maintain strict thermal stability to prevent texture loss or microbial growth during transit. Quality assurance labs operate in parallel with the production floor. Technicians pull random samples from each batch to assess moisture content, cooking time, bite texture, and microbiological safety. These samples are cooked and evaluated for structure, flavor retention, and resistance to disintegration. Texture analyzers apply calibrated pressure to measure chew resistance, while high-resolution cameras measure shape retention after boiling. If a batch fails any parameter, the corresponding lot is flagged in the system and held for further review or disposal. Cleaning and maintenance operations take place in modular shifts. All lines are fitted with cleaning in place (CIP) circuits, automated wash systems that flush tanks, hoses, pumps, and valves with caustic solutions, hot water, and acid rinses. This ensures hygienic conditions even when production is running continuously. Key areas like mashing stations, flour feeders, and packing heads receive manual cleaning daily, and critical equipment like extrusion heads are dismantled, brushed, sanitized, and reassembled before every major production run. Throughout the process, every detail is monitored by supervisory control and data acquisition (SCADA) systems. These systems provide operators with real-time dashboards showing dough temperature, flow rates, extrusion torque, cutter speed, par cooking dwell times, and fill weights. Alerts and automated corrections ensure that even minute deviations are caught and resolved without interrupting production. Historical data is stored and reviewed to improve yield, reduce waste, and maintain traceability. From field harvested potato to the final sealed pouch or frozen bag, gnocchi production at factory scale is a precisely tuned sequence of heat, pressure, shaping, and preservation, all balanced to protect the soft, pillowy character that defines this classic product. What begins as humble starch and flour becomes thousands of identical dumplings per hour, delivered with perfect form, flavor, and shelf stability. Lasagna production in a factory is a multi-phase, highly integrated process that combines pasta sheet manufacturing, meat sauce preparation, cheese blending, layer assembly, baking or pasteurization, portioning, packaging, and cold chain logistics, all synchronized to ensure consistency, safety, and scale. Unlike dry pasta or single-element products, lasagna is a fully prepared, multi-ingredient dish. This makes its industrial production uniquely complex, requiring extensive machinery and tightly controlled automation to ensure that every slice mirrors the expected texture, flavor, and structure. The process begins with pasta sheet production. Durum semolina flour is delivered in bulk and stored in silos. From there, it moves through pneumatic conveyors into high-capacity mixing vats where it's combined with water under vacuum. This vacuum mixing reduces air bubbles and improves dough elasticity. The dough is then extruded into wide sheets using continuous sheeting rollers. These rollers compress and stretch the dough between pairs of calibrated rollers, gradually flattening it to a specific thickness, typically less than 1 millimeter. Optical thickness sensors positioned along the rollers feed data into a closed-loop control system that makes micro-adjustments in real time. The continuous pasta sheet is then guided onto a conveyor that passes through a high-temperature dryer tunnel. This dryer uses forced hot air to reduce surface moisture and firm the sheet slightly without fully cooking it, which gives it the pliability needed for layering. After drying, the sheet moves into a cutting system. Depending on the product specifications, a rotary knife assembly cuts the sheet into wide rectangular panels, each aligned with the intended tray dimensions. A rejection arm automatically discards any sheets that are torn, folded, or non-uniform. While pasta sheets are being prepared, the factory simultaneously produces the meat sauce. Ground beef is loaded into steam-jacketed kettles equipped with high-speed agitators. The meat is seared first, breaking it into small crumbles. Tomato puree, tomato paste, oil, chopped onions, garlic, herbs, and seasoning are metered into the kettles through automated valves. The sauce is simmered while being agitated to prevent scorching and ensure uniformity. During this time, inline temperature probes and brick sensors monitor thickness, sugar levels, and viscosity. Once the sauce reaches its target consistency, it's pumped through heated stainless steel pipelines into holding tanks that maintain it at a constant temperature until assembly. In a separate mixing area, the cheese component is prepared. Depending on the recipe, this may include a blend of ricotta, mozzarella, and parmesan. Ricotta is delivered in cooled totes and mixed with stabilizers, herbs, and sometimes eggs in vertical mixers to ensure even distribution. Shredded mozzarella and grated parmesan are stored in silo-like hoppers connected to vibratory feeders that portion out cheese by weight for each layer. Now begins the core of the lasagna production, layer assembly. This takes place on a continuous assembly line with moving trays or belt-mounted mold forms. Each tray or mold is sanitized prior to filling and travels under a set of ingredient dispensers. First, a measured amount of meat sauce is deposited into the bottom of the tray by a servo-controlled nozzle that moves in a sweeping pattern to ensure full coverage. A vacuum depanner then places a single pasta sheet on top, aligning it precisely over the sauce. This is followed by a ricotta deposit nozzle that pipes a uniform, ridged bead of cheese across the sheet, which is then smoothed by a vibrating spreader bar. Another pasta sheet is placed, and the cycle repeats: sauce, pasta, cheese, until the required number of layers is achieved. The top layer typically ends with sauce and a sprinkling of shredded mozzarella and parmesan dispensed by oscillating auger heads that shake cheese evenly over the tray surface. Before baking or pasteurization, some lines include a brief compression station where a flat paddle gently presses down on the lasagna to remove air pockets and improve bonding between layers. The fully assembled trays then move on to the thermal treatment phase. If the lasagna is intended to be frozen, the thermal step may be pasteurization, which involves heating the product just enough to kill bacteria but not fully cook it. For chilled or ready-to-eat versions, full baking is performed. Trays enter a convection oven that circulates heated air at over 180 degrees Celsius. The line speed, tray height, and internal oven temperature are all controlled to ensure even cooking from edge to center. Internal temperature probes inserted in sample trays verify that core temperature targets are achieved and held for a specific time to guarantee food safety. Once cooked or pasteurized, the lasagna must be cooled rapidly to prevent microbial growth and lock in texture. This is done through a tunnel chiller, where trays pass through zones of progressively colder air, sometimes supplemented by glycol-cooled plates that pull heat from the tray bottoms. The cooling process must reduce the product from over 80 degrees Celsius to below 5 degrees Celsius within a few hours, which is regulated by airflow, dwell time, and temperature differential. Sensors at the tunnel exit confirm that each tray meets cooling requirements. Once cooled, the lasagna is portioned and packaged. If individual servings are required, the tray is sliced by ultrasonic knives that vibrate at high frequency, cutting cleanly through dense layers without dragging or distortion. For family-sized portions, The entire tray may be sealed as is. Packaging formats include vacuum-sealed trays, film-sealed thermoformed, packages, or sealed and labeled foil trays, depending on the target market. Modified atmosphere packaging may also be used for chilled products to extend shelf life. Oxygen levels are flushed and replaced with inert gases before the final seal is applied. Each sealed package passes through a metal detector and X-ray unit to ensure it contains no foreign materials. It then receives an inkjet printed label showing the batch number, production date, expiration date, and a scannable code for traceability. The labels are verified by vision systems to confirm placement, readability, and correctness. Any mislabeled unit is automatically rejected into a separate channel. From there, packages are grouped into boxes using robotic case packers. These cases are palletized by automated arms that stack them in stable formations, alternating layers for weight distribution. Stretch wrapping units seal the full pallet, and each is tagged with a warehouse tracking code before being moved to cold storage. Depending on the product type, it may be stored in refrigerated or frozen conditions. Pallets are managed by automated guided vehicles that transport them to pre-assigned racks in high-density storage systems, where inventory software tracks position, age, and destination. Throughout this process, the factory uses a SCADA, supervisory control, and data acquisition system to monitor every critical variable. Dough hydration levels, pasta sheet thickness, sauce viscosity, cooking times, and packaging seal integrity are all tracked in real time. Historical data is stored and analyzed to identify patterns, correct deviations, and optimize throughput. If any parameter falls outside the designated range, alarms are triggered, and the system automatically isolates affected batches for inspection. Cleaning and sanitization cycles are embedded throughout the plant. Clean-in-place systems run through the pasta extruders, sauce kettles, and piping lines at scheduled intervals. Belts, mixers, and conveyors are cleaned using automated foamers and high-pressure rinsers between production runs, often overnight. This ensures the plant can shift from producing meat lasagna to vegetarian or gluten-free variants without cross-contamination. Every few hours, quality assurance teams perform manual inspections of randomly selected trays, assessing factors such as layer adhesion, ingredient distribution, flavor profile, pH level, and slice integrity. Cooking tests are conducted to see how the product behaves in a domestic oven or microwave, ensuring the consumer experience matches factory standards. The entire process, from flour and raw meat to finished boxed lasagna, is designed for speed, consistency, and hygiene. Trays of lasagna move continuously through a loop of automation, blending traditional culinary elements with industrial engineering. The meat must be savory but not greasy. The pasta should remain tender after reheating without breaking apart. The cheese should melt and set without seeping or becoming rubbery. Each of these qualities is maintained not through guesswork but through precise mechanical control over every movement, temperature change, and ingredient ratio. In the high-output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counterpressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for Brix levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning in place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine: syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola-based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup to water ratio down to 0.1% so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and pass through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber, where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume. turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry where every gram of input is measured, every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proofer climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edge slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft-tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, a mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow-wrap sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station, where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, the seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause.